Hello everyone, I am Atharva Peshkar and my project aims to evaluate the anatomical correctness of the obtaining skeletal shape from outside model. But before we dive into the details, let's understand what are anatomic skeleton models and why do we even need them. Anatomic skeleton models are 3D models that provide a highly detailed representation of an individual's anatomy. Today, skeletal anatomic models are widely used in biomechanics to study how the forces transmit through different bones and joints, in various clinical applications like positioning, workflow automation, image-guided interventions, including radiation therapy, for computer graphics to create realistic models of the human body for video games and movies, and for educational purposes to create interactive learning experiences. The following types of models exist today. The first one being data-driven bone models. They are developed by fitting 3D template models to 2D images like X-rays. However, today they are just limited to individual bones or bone groups. The second one being the personalized anatomic models. These are created using imaging modalities like CTs and MRIs, but they are not representative of the general population and cannot be inferred from the skin surface. Third is the physics-based anatomic models, which simulate the growth of tissues and bones, but usually they are not learned from or validated against the medical data. Finally, we have the obtaining skeletal shape from outside, or the OSSO model. This is the first statistical shape model for predicting whole skeletons from the body surface. This was trained on a dataset containing different body shapes, and so this is representative of the general population and provides a detailed anatomy for the patient based on their body shape. However, the OSSO model has certain limitations. One, it was not evaluated on real 3D medical data or medically validated data, but on 3D models that were created from 2D data, like X-rays. And second is that it was not evaluated on individuals who are morbidly obese or extremely skinny. Which raises the question, is the OSSO model accurate enough for clinical applications? To answer this, I evaluated the model against the 4D extended cardiac torso phantom model, also known as the 4D XCAT phantom model, which was learned from CT scans of male and female anatomies and is widely used for medical imaging research and treatment planning. For this study, I generated 10 male and female phantom patients of different ethnicities, ages, and BMIs. You can see the patient details in the following table. Coming to the evaluation metrics, after a thorough literature survey, I could not find a specific metric for evaluating a whole 3D skeleton model, and so I used the standard metrics that I used to evaluate individual bone or organ models. The metrics that I used were directed Hausdorff distance, that gives us the maximum error between the closest points on the ground truth and predicted skeletons. This is a similarity metric and it is preferred for evaluating the alignment and boundaries of complex 3D objects. The second one being the root mean squared error, that gives us the average error between the closest points on the ground truth and predicted skeletons. Coming to the methodology, for every patient I first created an XCAT phantom. Then I created a 3D skin mesh model of this phantom. Finally, I used the OSSO model to predict the skeleton of the patient given their 3D skin mesh. Once I had the predicted skeleton and the phantom skeleton, I hollowed out both of these meshes. This was to ensure that no errors are introduced due to the vertices of these models lying inside the model rather than lying on the surface of the model. Finally, once both of these meshes were hollowed out, the predicted skeleton was aligned with respect to the ground truth phantom skeleton by rotating, translating, and scaling it appropriately. Now, these skeletons were ready for evaluation. These are some of the skeleton figures indicating Hausdorff distance errors. Here you can see in the figure on the right that even though the OSSO and phantom, both of these skeletons were in the lying down position, the poses between the OSSO and phantom skeletons are different. And this also reflects on the figures on the left, where you can see that warmer colors indicate lower errors, whereas cooler color indicates higher errors. And you can see near fingers and toes, the blue color indicates a high error, while the skull has a relatively lower error. Uh, since the wrong pose could have led to increased errors, I also considered anatomical landmarks like the coccyx or the tailbone and the iliac crest, which was unaffected by the different position of hands and legs. Here you can see that the tip of the tailbone has shifted by around 5.2 centimeter compared to the ground truth, whereas the iliac crest on the left, which is highlighted in dark blue color, indicates a high error of about 4.7 centimeter compared to the ground truth. Coming to the results, for both males and females, the general trend is that a high BMI introduces high errors in the predicted skeleton, whereas a lower BMI leads to lower errors. Moving on to the conclusions, the medical literature and guidelines on surgery and radiation therapy consider 5 millimeters to be the maximum acceptable error in positioning, whereas the OSSO model had an error of approximately 44 millimeters for a fixed anatomical landmark, unaffected by the position of limbs, thus making the OSSO model unsuitable for clinical applications that rely heavily on bony landmarks. Thank you.